So welcome back. That's our lab 7 from week 7, and that's our third video. So we finished last video. We're building our table that will be our z-test, and we ended up saying that before we go to the next step, which is to compute the z-statistic that will allow us to compute the probability of getting the score, it's useful to actually draw the distribution. And here it is. So we have the distribution, which is normal. It's a normal distribution. Let me try and frame it here. Oops, this is not going to be good. So we have the center at 100, and we have the score of 118 right there also illustrated. And what we want to know is the probability of getting 18 or higher. So we want the probability, the area under this curve there, 18 or higher. But it's because this is a normal distribution, it's nice to get the standardized value for that 118. How many standard deviations above the mean that particular value is, that particular mean value is, right? So we can compute the z-score, just like you learned last class, all right? So let's do that and see what's the z-score that corresponds to this particular 118 score. And then from that, we can get the probability, which is the p-value of getting that particular score or higher. If that probability is very, very low, it's not usual to get that value of 118 if nothing's going on, if the distribution has a mean of 100. And that will lead us to reject the null hypothesis in favor of the alternative hypothesis that indeed getting 118 under the null hypothesis is not very likely, right? So let's go on and compute that. So because the distribution is normal, the test statistic we want is a z-score. A z-score will tell us how far in standard error units the observed mean is from the expected mean value under the null, which is 100. To compute this statistic, we need the observed mean value, the x bar, which we have here, the expected mean value under the null, which we have here, and the standard error, which we have right there. So we will add the z-statistic to our table. So you know how to compute the z-score. It's the observed score minus the mean score, in here is the expected mean value under the null, divided by the standard error, which we have right there. So we're adding that to the table as well. So here's our z-statistic. So this, our z-score, comes out to be 16.66. Such a high z-score means that the observation is usually far from the center. Recall that more than approximately 2 standard deviations is already unusually far, because remember, 2 standard deviations above the mean and below the mean has 95% of all of the data, right? Leaving only 2.5 and 2.5 in each tail, right? So it's not very likely to even have anything above 2 standard deviations. And here we have that score 16 standard deviations, standard errors above the mean. Therefore, we should be expecting a very small likelihood of observing this particular value of IQ if the null hypothesis was true, right? It would not be likely if we get multiple samples from a population that actually has the average of 100 to observe 118. It can happen, but the probability would be very, very low. So let's compute the probability of getting that particular z-score or more extreme. Again, now we'll use the p-norm that you also learned last time. We'll put the z-statistic there, and we want the upper tail, right? The particular finding we had, or larger. That's why we're saying that we were setting lower tail to false. In this case, we want larger. It's a directional hypothesis, and the hypothesis is that the score will be that particular value or larger, greater than 100. That's what we hypothesized in the alternative hypothesis. The applet we saw in class is very useful also to visualize those distributions, so you can play with that too. Now, what we just looked at is a one-sided z-score. And just like I pointed out above, Here is the code, the base code that you want to use every time I ask you to compute confidence intervals. And here are the base codes if you want to compute one-sided z-scores, directional z-scores. Here is the one that you would use for computing, for testing alternative hypothesis that the mean is greater than a particular value. It doesn't need to be 100. 100 is specific to this particular example. But any test that you expect the mean to be greater than a particular value, that's the one you're going to use because we're setting the lower tail to false because this is the probability that we want to compute, the particular value or higher. If the expectation is that it would be less than 100, we would have to be expecting a value that's less than 100, and we would be interested in the lower tail. So then in that case, we set the lower tail to true, but the full, what you copy is the full thing there. And again, just like you did for the code, for the confidence interval, I ask you to pause the video at this point and see which pieces of this code that you would have to modify according to the particulars of your problem. For example, if you're using a different data set, this needs to change. If the null value of the mean that you expect is not 100, is 20, 30, 0, then you change this piece, right? The name, every place that shows the name of the variable, you have to change, right? The rest is all the same. And you will practice using this particular code and modifying it in a little bit. All right, so here's our table. We have a p-value that's pretty low. It's 1.3 times 10 to the negative 62. So 61 zeros, 136. So pretty much zero probability of seeing a score of 118 or higher, a mean score of 118 or higher, if the mean of the population is actually 100. So this is what this p-value means. If the p-value is low, we say that it would be very unlikely to observe the data that we observed, an average of 118, if the null hypothesis were true, and therefore we reject that null hypothesis. If on the other hand, the p-value was high, greater than the magical 0.05 standard score, we would say that it is indeed likely to observe the data if the null hypothesis were true. It's just sampling error. I just didn't get the 100 sharp because, just by chance, you might not get that if you sample repeatedly from the population. And hence, we would not reject the null hypothesis. All the information we need is on the last table we generated. It is a summary of steps 1 to 5, so it contains all we need to make a final call. For that, then, we need to consider a cutoff value, and again, that's set to 0.05. Because in this case, it's so close to 0. It's 0.00061 zeros, 1. It's clearly not, right? Very low. But the cutoff value is actually 0.05. Anything that's less than that would be grounds for rejecting the null hypothesis. Now, step 6 is to make a decision and interpret things in the context of data. The decision would be here: the smaller the p-value, the stronger the evidence against the null. And since we have a tiny p-value, we have very strong evidence against the null hypothesis. Therefore, we reject that in favor of the alternative hypothesis. Data provides convincing evidence that the average IQ score of mothers of gifted children is higher than the average IQ score for the population at large. Now, the test that we just ran is a one-tail test because our hypothesis was directional. How about two-tail tests? So the reason we ran a one-tail test is because the researcher's question, and more importantly, the hypothesis, was directional. So we were expecting that mu was going to be greater than 100. We had a directional. Often, instead of looking for a divergence from the null hypothesis in a specific direction, so either a greater than or less than sign, we might be interested in a divergence in any direction. We don't have a clear expectation that it's going to go just on one side. We call such hypothesis a two-sided hypothesis. or you might also hear of them being referred to as a two-tailed hypothesis as well. The definition of the p-value is the same regardless of doing a one-sided or two-sided test. However, the calculation becomes slightly different and ever so slightly more complicated, since we need to consider the probability of an outcome at least as extreme as the observed one in both directions away from the mean. So let me try to show you in a concrete way how one-tailed versus two-tailed tests would differ. So the one-tailed, the research question driving the analysis, is directional. Do mothers of gifted children have higher IQ, not different, higher IQ than the typical population? Or do mothers of gifted children have a smaller IQ than the typical population? Then the hypothesis will be directional, mu greater than 100. Now the two-tailed, the research question driving the analysis, is not directional. Example, do mothers of gifted children have an IQ different from the general population? Note that all we changed in the description was the nature of the question. It is no longer directional. That is, the question implies that there is an expectation that the level of intelligence of mothers of gifted children will be different. Could be higher, could be lower. Who knows? Maybe it's not about genetics. Maybe it's something environmental. If the mother has very, very low IQ, maybe kids become sort of savvier to compensate, right? So you could have an expectation that things could go in either direction. This will have implications to how we set up the test, set up and test the hypothesis. Now let's see what changes. So the null hypothesis would be, again, that mu equals 100. The alternative hypothesis is that mu would not be equal to 100, would differ from 100. So in no specific directions. Steps 2, 3, 4, and 5 are exactly the same. The only thing that changes is how we compute the p-value. If we actually wanted to do a two-sided hypothesis test with the existing data that we just discussed, our p-value should reflect the probability of x bar being greater than the 118 or less than, on the draw, or less than 81.2. Right? So it would be the probability of having something extreme to one direction or the other. Where am I? So 181.8. All right, so those two tails is what I need to compute. You might be asking, how did I come up with the 81.2? And that's the same distance between 100 and 118 in the other direction, right? So I simply, the distance between 100 and 118 is 18.2. If I subtract 18.2 from 100, I go all the way to the other direction, all right? So I need to compute the probability of the two sides. In general, if you're looking for the cutoff values of these two-sided hypothesis tests, all you need to do is to travel the same distance away from the mean to the two sides. No matter which one you get, if the mean is this one or that one, you would have to compute the other side. But really, this is just for you to understand things conceptually, because in reality, because the distribution is symmetric, the probability of getting a value of 18 or higher is exactly the same as the probability of getting 81.8 or lower. So really, all we have to do is to compute the p-value just as we did before and multiply it by 2. So it's a stringent test, basically, but that's all that changes. So instead of simply computing the p-value as we did before, right? So we have the p-norm z-stat for lower tail, and then for negative z, because it's the same z, it's just negative counterpart, and sum the two, we can simply do 2 times the probability that we compute for the one-tail test. So to put everything on one table, the code is exactly the same from before. All that I'll change is multiply the last probability I compute by 2. Run the code, and we have the probability for a two-tailed test. All right? decision is the same as before, and we'll come back to practice that with a different